Anyway, so let's see. How far did I move over? Well, or how much? What's the time here? Well, the time had better be such that the argument, if this all gets to 0, because that's that part of this curve, when what? When x equals lambda over 8. So if I say k times lambda over 8 equals omega t. Omega times, what time is it? Oh, that's what I'm trying to look for. So that means that t has to equal k lambda over 8 omega. Anyway, so I can figure out what t has to be by going through all these machinations. And this is a positive number. So good, I got my sign right. Anyway, so I told you there's a proliferation of symbols, and not just symbols, but of different physical quantities when you get to waves and oscillations. And it's true. There's 10 ways to write the same thing. There's a lot of degeneracy. And that's okay. But just be aware of the fact that there are more variables around than a number of distinct attributes of the wave. You can't separately specify all these different values. They have relationships between them. You have to make sure the relationships make sense. But okay, anyway, so here, this is the time that corresponds to this picture. All right, so the wave is moving to the right. Whenever you've got a wave equation of sine or cosine or whatever you've got, and it's kx minus omega t, that's a wave moving to the right, where the right is the positive x direction. If it's kx plus omega t, it's going to the left. Just everything's the same, just put minus signs in front of the, well, if you like, you split the direction of your time x. So waves move to the right, they have a negative sign right there. And what is the speed of the wave? Well, let's think about that. The speed of the wave, which they often call the wave velocity, even though it's sort of a bad thing to call it because we're talking only about the magnitude of its speed, really. Like if the wave were moving to the left or right, I would still define v the same way. So just be aware of that. But anyway, the speed of the wave is equal to what? Well, I can figure out, the simplest way I always remember to figure that out is that I know how long it takes to go through one cycle, and I know how far it goes in one cycle. It goes lambda in one cycle, and that's in meters. That's how far it goes, right? And it takes one period to get there. That's how long it takes. The velocity is meters per second, right? The speed is meters per second. So that is the wave speed. That's how fast the waves go. And when it's going, and it goes right if it's a minus sign, it goes left if it's a positive sign. So that's just generally the math you're going to see over and over and over again with waves. Equations like this. There might be an added phi over here, which would just, if I added a plus phi, then it would shift all these pictures from every moment in time a little bit to the left, I think. I'm telling you the right thing. It's positive phi. And same thing for pictures of x for y versus t. Anyway, all right. So that's the basic math. I'm not going to go through the derivation of this, but depending on the physics of the problem, depending on what's causing the wave, you can go through the process of calculating how fast the wave should propagate. Different media have different wave speeds, like sound, speed of sound. What is the speed of sound about? Is it faster than the speed on this rope? So I can actually see the speed on this rope. It's fast, but I can see it going back and forth, right? It's I don't know, tens of meters a second. How fast is the speed of sound, though? So the speed of sound is fast as the speed of light? No, the speed of light still is infinite, right? Speed of light is what, 10 to the 8, 3 times 10 to the 8 meters per second. Speed of sound is, it's Mach 1, right, at sea level. Speed of sound is like 300 meters per second, about. It's fast. But there are things that go faster than that. In fact, I shot what was that? A ping pong ball faster than the speed of sound, just barely, a few lectures ago, right? So it's a speed that's, like if you're far away from if you're watching a baseball game and you're far enough away, you get different time of flight for sound from different speakers in the stadium because the sound is finite, and you can actually detect it. Something hits the ball, you get the crack of the ball after you see the ball flying, right? Because the light gets to your eyes much faster than the sound, right? On something that's that quick, where you can actually detect it. Most of the time you don't notice. In fact, if you watch videos nowadays, they desynchronize the audio and video so much, but you don't really notice that much because our brain just sort of puts up with it. Because things take long sometimes. Go ahead. Yeah, I know where it came from. I don't care. But it's a little strange to me because I'm used to like when they were lined up. But anyway, so speed of sound is finite, and you can have. And so when we do the Doppler shift in a few minutes, that will relate to the fact that it's a finite speed, and you can actually detect effects. You can measure the effects of motion of observers or listeners and the things emanating these waves. Their motion can be comparable or big enough compared to the speed of sound that can affect the way things sound, right? Okay, so one calculation. I won't go through the derivation like I said, but I'll go ahead and just state the result and let you look at the book if you want to see where it comes from. But you can calculate how fast a wave will travel in a rope. And it turns out to depend on a few aspects of what's going on with the rope. One is how massive the rope is. If you have more mass per unit length, you think that would speed up or slow down the wave? Yeah, it slows it down. The more massive it is, the slower. It's just like an oscillator. The frequency of oscillation goes down when it's more massive, right? And also, it also depends on, like, the restoring force has to do with how hard you're pulling the rope. So right now the rope's being pulled. It's under tension, right? And if I see how fast a ripple goes back, a wave goes back and forth in the rope, it's pretty quick. But if what I do is I slacken it, so now if I go this way, so now there's less tension on that side of the rope and more tension on that side. Now the rope will be, the wave should get faster on that side and slower on that side. I'm not sure you can see that. So I'm also going to hit the back of the head with the rope and it comes loose. Is it working? No? Go a little further. This is not an ideal rope, right? I'm stretching the heck out of it, right? I wouldn't be able to do that if it were an ideal rope. I should have tried this before class. It's sort of working. It's slowing down a little bit. It's working a little bit. It's going a little slower. I know you're humoring me, so I'm going to move on. I don't blame. But yeah, so it's moving slower over there and faster over there. Why? Because I changed the tension. And so if you go through the math, as the book does, it turns out that yes, indeed, the speed of a rope, the speed of the wave. It's not the speed of the rope, right? The speed of the wave as it travels down goes like, again, it's always a square root. Right? There's always square roots with these waves in oscillators. Square root of, and I'll use f sub t to represent this is the thing we used to call t. This is tension. But I want you to think it's the period. We're just running out of symbols. That's the problem. So this is tension of the rope. And the bottom I get what we used to call lambda, but now we're using lambda for wavelength. So now we call it mu. By mu I mean mass per unit length. Okay? So that's just that's the same thing that we said before. It's the mass of the rope divided by the length of the rope. Right? The bigger that is, the slower the wave speed, as you would guess. Right? And the bigger the tension. The harder I pull on it, the faster the wave speed is going to be. Makes sense. Okay. Which two velocities? Oh, these two velocities. So these two velocities are the same. If what I mean, so let me say it this way. These equations right here, I was doing, and this is just specific to these two pictures, so don't worry about that one. But and this stuff over here is particular to the particular time I chose. But this, k is 2 pi over lambda. Velocity of a wave equals lambda over capital. The wavelength over the period, wave, all this stuff. This is totally general for any wave. Right? These are always true type equations. This is only true for a rope. In particular, it's only true for a rope. It's only true for transverse waves on the rope. It's only true for waves that where it's the oscillation is in the vertical direction, say, and the rope is strung out in the horizontal direction. It's not true for waves like this, compression waves in the rope. It's not true for sound waves. It's not true for water waves. It's not true for light waves. Right? This is only true for transverse waves in the rope. For different physical situations, you'll get different relationships of this type. But it's always going to be the case you can use these kind of equations to describe the wave that results in whatever medium you're talking about. Yeah. So, okay. Yeah, good question. Sorry? Yep. Mu is mass per unit length. And I just changed it to, well, the book did. The book changed it from mu from lambda because we've already used lambda for wavelength. Yeah, there's just not enough symbols. Okay, so what about power? Well, there's a couple things to say about power. One is that we've already seen power in the context of, I don't know, doing work on something, right? And so how much power is done. All power is how much work per unit time, work or energy per unit time is being transferred from one place to another. Well, waves transfer energy. Therefore, they provide power, right? So if we say, well, how much power is being transmitted through some point along the rope? If I say at this point, let's call that point x equals 0, and say, all right, how much power is being transmitted through? Well, the book does a derivation for this. I'm going to do a different derivation really quick based on a calculation I did a couple lectures ago. So a couple lectures ago, I remember we said, well, let's think about an oscillator, mass on a spring, and let's calculate what the energy is, the kinetic energy is in this thing, and what the potential energy is in the spring. And I said, well, okay, let's start off. First of all, we've got our x as a function of time now, right? And I said, well, x as a function of time, it looks like this. X equals some amplitude times cosine, let's say, it doesn't matter, let's use cosine, times omega t, right? And I said, well, and so what about the velocity as a function of time? What does that look like? Well, we know what that looks like. If you start off with cosine, then you get it's negative sign, it's negative slope, it's negative sign. Good. And what's the amplitude going to be there? Oh, I should call the amplitude. What's the highest part of the curve for the velocity? That's going to be a times omega, right? Because now you get v goes like omega a, the minus sign in front of sine omega t. And then we said, oh yeah, we know the definition for kinetic energy. Potential energy. Kinetic energy is 1/2 mv squared, right? So if I say, what's the potential energy? Let's do both energies. Let's do kinetic energy first. Kinetic energy is going to be 1/2 mv squared, right? And that's omega squared a squared. This is not big enough. Let me write this bigger. You guys can see it. So what's the amplitude going to be? 1/2 mv squared. V has a coefficient in front of omega times a, so it's omega squared a squared. And what does it look like? It's this squared, so it goes like this, right? And then we do the same thing. I didn't quite make it properly. We do the same thing for potential energy, and we find, lo and behold, that potential energy has the same amplitude. Once we realize that omega squared equals k over m, then you get a k up here, 1/2 k times x squared. It's the same, but it's shifted over, so it goes like this, right? And then we said, we got to add up together. Well, that means that the energy inside of some oscillator is just given by 1/2 m omega squared a squared. So if we ask the question, well, then how much power is being transmitted down a rope that's made up of a bunch of oscillators? Well, first we have to figure out, like, this is how much energy there is inside of an oscillator that's going back and forth with some amplitude a and some frequency omega, right? But this is the total mass of the oscillator. Well, now we've got this concept of mass per unit length, of mu. We can say, well, this is, so energy, so the total energy in an oscillator, what is that? It's equal to, what did I say, 1/2 m omega squared a squared. In a rope, if I say energy per unit length, so what's the energy per unit length in a rope, right? It's got some wave that's traveling down it. Well, it's going to be this, but instead of this, it's this over L. Well, capital M over L is just the mass density, the linear mass density. So you get 1/2, what is that, mu, we called it, mass density, times omega squared a squared. And now if we want to know, well, how much power is there on average? Is that, how much power on average is being transmitted through some point right here as a rope? And so some wave is traveling that way. That's how much energy per unit length you've got. I want to multiply, I don't want energy per length, I want energy per unit time. So if I have this thing that's got length and I want time instead, well, if I want to relate length and time, that's the velocity. So if the wave has some velocity v, and I multiply it by that, that'll tell me how much energy per unit time is traveling through some point in the rope. So this is what I consider a simple derivation in the books. You may hate it, I apologize. But when the test fails, you get your answer, which is the average power that's being transmitted down the rope with your wave is equal to this times the wave speed. 1/2 mu omega squared a squared times v, the speed of the wave. Reassuringly, I get the same answer they did. So it gives me some confidence that that's all right. Yeah, there you have it. And it makes sense, right? The bigger the wave speed, the more power you're going to get, the more energy is going to be transmitting through some points on the rope, right? And the bigger the amplitude, the more power you're going to get, right? And so on. So this is power. But there's a related idea for waves we call intensity. So power is the amount of energy per unit time that's being transmitted by the whole wave, right? You've got some rope, and there's some wave going down the rope, traveling along, going through some point, and there's a total amount of power that's being delivered through, from one side to the other of the rope, or through that point in the rope. But if you have a different kind of a wave that has a two-dimensional wave front, like a sound wave, forget I'm amplified, if I'm sitting here and I'm talking, right, out of my head is coming a bunch of spherical waves, right, of sound. The wave fronts are going to be, and what do I mean by wave front? In the context of, so it's not the wave on the rope, I talk about the crest of the wave, the high point, right, and talk about that thing moving along. You can think about it that way. I'm talking about sound waves, then I might talk about a surface where the compression is greatest, or so the pressure is the greatest, or something, or where the displacement is the greatest. So when air is displaced, so air is being displaced, it's a longitudinal wave. As I talk this way, if you take a snapshot in a moment in time and see that right here the pressure is really high, and right here the pressure is really low, and here it's really high. Well, where the pressure is high, how did it get high? It got high because from either side of it, air molecules were moving; they were just being displaced toward the high pressure area. So you can think of either in terms of displacement, or you can think of it in terms of pressure. Sort of complementary ways of thinking of the same thing. And that picture up there of the masses on the springs, the longitudinal wave picture, that's what's going on, right? The air molecules get close together over here, and they get rarefied over here. So low pressure, high pressure. So when I'm on a wave front, the surface I'm talking about is the surface of constant pressure or constant displacement, whichever variable you prefer. And that is going to be a spherical wave. In the three-dimensional world, you have some source of waves in the middle that's producing these waves are going out. You have some speaker right here, and waves are coming out. Well, they go out in a spherical pattern, right? And they go out like this, right? And so I'm just drawing an equator on it so you can see this is a sphere, not just a circle, right? So it's going out in all directions to the sphere. The distance from one to the next of those crests, right, is just the wavelength, right? That's the wavelength. And if we ask what's the power doing, well, the power is going to be getting, well, what is power? Power is, the intensity. Let me get this right. The power is energy per unit time. The intensity is the energy per unit time per unit area. So if I ask, okay, I've got some little unit area, some little patch right here. How much power is being transmitted through that little patch of unit area, meter by meter, little meter by meter patch there? Well, can you see that less power is going to be being delivered through this here than through this over here? Because however much power this guy is delivering in the center, the source of these waves, right? That power is being distributed evenly around this whole sphere, the surface of the sphere. So if you're standing closer to me, I'm going to be louder. Your ear, which is the same size, no matter how close to me you get, so it's kind of like the thing that you're detecting, this is where power's going in, right, your ear. If you get your ear close to my mouth, it's going to be a lot louder. You get more power, right? And that's an awful thought. And so you step back, it's going to be quieter. How much quieter? How much less power will you get if you step back? You go twice as far away. Well, the surface area has gone down by 4 times, right? Because the surface area of the sphere was like r squared. It's 4 pi r squared, right? So that means that the intensity, I know we used capital F for some other things in the past, but right now we use it for intensity. Well, I'm just talking about the average power per unit area. Well, this is just going to be whatever the power is from that source divided by the area of the spherical wavefront. So that's 4 pi r squared. So it goes like 1 over r squared. Okay. So when you're dealing with a rope or some linear medium, and all the power is moving along, it's not spreading out, it's always like concentrated on this rope, right? Then you don't have to worry about these ideas so much. But when you're thinking about sound waves or light waves, things like that that go out in a spherical wavefront from some source, then it's worth thinking about intensity, where you say, what is the amount of energy per unit time passing through some unit area? Okay, cool. All right, intensity. So what's next? So many concepts, lots of concepts. So the next thing I want to bring up is interference. And in particular, so the more general idea, and I'll focus in on interference. The more general idea is the idea of linear superposition, which is a fancy word for you can just add waves up to get what the final wave looks like. We've seen that a lot in this class already. Lots of the concepts in this course. If you want to know if you want to apply Newton's second law, how do you do it? Well, you need to know what it's F equals ma, but it's not just any old F, right? What F is it? It's the net force. And by net, I mean the sum of all the forces. But it's not just any old sum, it's a vector sum. Okay, fine. But it's a sum, and some of the contributions might be positive, some might be negative. In other words, forces can cancel each other out, or they can constructively add, right? It can be destructive or constructive. And in the same way, waves work just like that. It turns out it's this is a really important realization because it allows physicists to solve a huge number of problems, and engineers to build a huge number of devices and things, understand really complex problems, by breaking them down to easy pieces and then just summing out the answer to get the right answer at the end. So what am I getting at? Well, in the context of an oscillator, so let's think about this in terms of an oscillator first. So let's think about it in terms of two tuning forks up here. So I'm going to draw a picture of what I'm going to do. I'm going to take two tuning forks, and they have slightly different frequencies. I'm going to change them so they have different frequencies, so that they will they'll oscillate like this. What am I plotting? I'm plotting as a function of time. That's myself a little room. Plotting as a function of time some displacement of the tuning fork. It's wiggling back and forth, right? And for one guy, it'll look like this. See if I can pull this off. It's kind of a hard drawing to make. Well, I'm already messing it up a little bit. It's kind of groove. This is supposed to be a perfect sine wave. And now I'm going to draw another perfect sine wave. This one, I'd like to be slightly different in frequency. So maybe it'll start off lined up with that one, but it'll reach a peak a little bit later. This got a smaller frequency. And let's say the amplitudes are the same. So this is amplitude A, here's amplitude A. So the amplitudes are the same with these two waves, but what's different is the frequency. A little bit smaller here. So let's see, it would wind up here, and then it would wind up twice as far off over here, and then it would be like way over here, over here. Oh, yeah, I myself. What's going on? All right, I'll keep going. All right, so what do we get? Well, if I draw this guy like this, and then have him his peak over here, then hit his peak over here, then hit his peak over here. All right, well, I made this guy even smaller in frequency than this guy compared to what I'm shooting for, but that's okay. So if I add these together, what am I going to get? And when I give myself enough room to draw below, so when I draw what I would get by adding these together, by taking this, adding it to this, and drawing with a different color on the first graph. Oh, except I've got no other colors. So maybe that's not going to, oh yeah, that's my color. Here we go. Someone's been pilfering my chalk. I'm telling you. Yeah, and chalk is cheap, but if I don't have it, it's no good. All right, people even boo at that joke. I mean, usually I get some kind of reaction, but it's true. Somebody just stealing my chalk. I know times are tough, but come on. Anyway, okay, good. So this starts off in phase, 0 plus 0 is 0. What am I doing? I'm adding this plus this. I'm adding the height to the height of this at every moment in time. What do I get? 0 plus 0 is 0, right? So it starts off right here at 0. Well, now it reaches a peak here, but it's not quite reached a peak here. This guy's reached a peak over here. Anyway, so what happens? Well, they start off pretty much in phase. So it gets pretty big. These guys are both big and positive in the beginning. And now this guy goes through 0 here, and he's negative here and positive. So they go through 0 someplace here. Let's see, if I do this right, he goes through 0 someplace right here. And then, let's see, they go through 0 again. Why is this? So what I think I'm going to do is just approximate what I'll get, and then I'll show you that, and I'll assert this is what happens, rather than spend like 10 minutes seeing a very accurate picture of what this looks like. But what happens is you start off with things that are pretty coherent and lined up, they're constructively interfering. This is doing almost the same thing this is doing. So when you add them together, you get twice the thing you started with. But by the time you get over here, this guy's peak is close to his trough. See that? He's big and positive when he's big and negative. So they tend to destructively interfere. So the upshot is that you get a wave that does this. It tends to start off with a big amplitude when they're lined up, but because they have different frequencies, they get out of alignment, they get out of phase. At some point, they go very close to 0. The sum of the two. So again, the blue chalk, the thing I just drew, again, I apologize for, you can't detect the colors, but the second curve I drew is the sum of this plus this. And what you wind up with is a curve that is wiggling twice as fast, but it's very slowly changing its amplitude. See, it looks like that. See that? So you wind up with the product of a slowly changing sine wave and a quickly changing sine wave. And you can look up in your favorite calculus text, the half-angle formulas and all these things, the trigonometric identity. But when the dust clears, what do you get? You find out that the resulting waveform looks like this. So I just said, all right, if we start off with, if y of t, or whatever, x of t, I guess, equals a cosine omega t, and this is omega 1, they have different frequencies, so let's label omega 1 and omega 2, plus a cosine of omega 2t, well, I can rewrite this as a product of two sine waves, or cosine waves, as the case may be, and they have the property that the frequencies of these two guys are going to be the sum or the difference of the original frequencies. Anyway, so there's all this complicated stuff going on, but the picture is pretty simple. What you wind up with is just a product of a slowly varying sine wave and a quickly varying sine wave. So what does that look like? It looks like, see, I'm just going to copy it right off my sheet so I don't get all the factors of 2 in the wrong place. You get cosine, and you get 1/2 times the sum of the two, omega 1, it's the difference of the two, omega 1 minus omega 2, and then you